Good afternoon, everyone. Thank you for joining us today for the webinar. If you haven't joined us previously, we are SUT Plus, the developing young professional subset of the Society for Underwater Technology. Today, we have Joe Nicolette, the Vice President of Planning and Ecosystem Services with us. He will be speaking to us about net environmental benefit analysis-based comparative assessment. And if, Joe, you're ready, you can start your presentation.
Okay, no, that sounds great. Would like to welcome everybody again. Good afternoon. And I'm going to go through a little bit. I'm going to talk about net environmental benefit analysis as it relates to comparative assessment and offshore decommissioning. And I'm going to give a little bit of background on myself, as well as some of the key aspects of this approach. And towards the end of the presentation, I'll be giving we're showing a short video that sort of really gets a lot of the information across in a short amount of time, a lot more than it takes to go through and present a lot of this. I've been an environmental consultant for over 35 years. I was a certified fisheries scientist, and worked primarily in the area of some of my first work was on the Exxon Valdez, and from that point in time worked on one of the first net environmental benefit analysis projects related to environmental decision making for, in this case, it was options to clean up sections of Prince William Sound. So from that point on, back in about 2004, 2003, worked and co-authored with United States Environmental, some folks from the United States Environmental Protection Agency and Oak Ridge National Laboratory, a framework for NEBA as it's used for looking at site remediation and how do we make decisions. And that approach and framework is recognized by EPA Science Advisory Board, the National Oceanic Atmospheric Administration in Australia, and several others. And as part of this work, one of the things that evolved was the evolution of ecosystem services and valuation. And I'll talk a little bit about that later, but really worked on these approaches and how do you do some of this valuation work prior to them being codified into the Oil Pollution Act in 1996, as well as the Superfund, the Site Cleanup Act in the United States, as well as their incorporation in 2008 into the Environmental Liabilities Directive in Europe. So and really with this approach, I've taken this approach and about 10 years ago started to recognize a good application of this approach to offshore decommissioning. And then I'm going to talk about some of that experience today and working on this. I think I've worked on 13 different sites, multiple in the North Sea, multiple in Australia, Gulf of Mexico, California coast, as well as Gulf of Thailand. So I've worked on a lot of projects, a lot of states in the US, and really worked a lot on the ecosystem valuation projects in I think 18 different countries. And I've served as an expert witness in relation to these methods. So what I'm going to do is I want to talk about what am I really going to present and talk about today is, really want to clarify NEBA in the context of a comparative assessment, because in the UK you hear a lot of the term comparative assessment, as well as elsewhere across the world, as a general approach to how do you make some decisions and come up with some decisions. And then, and what we want to do with those decisions is understand what the consequences of our actions are going to be. And then I will talk about then what are the types of inputs that we look at to help produce a compelling comparison of alternatives, and really think about ideology versus science. We want to understand what are the true impacts and benefits as well as negative impacts associated with different actions, and sort of look at what are some of the predisposed ideas. For example, like an OSPAR of full removal is the main, is the initial starting point. And when you think about that, what really are the benefits of that compared to the detriments? So we'll talk and we'll look about that a little bit. And I'm going to talk about ecosystem service benefits and really what they are and why they're critical in differentiating between options. And because what happens then, if you ignore these ecosystem service benefits, some actions can actually create significant detrimental impacts compared to any of the beneficial aspects that they might actually produce. So I'm going to talk now about ecosystem services and what are ecosystem services. Ecosystem services, the Millennium Assessment was conducted back in the mid-2000s by the United Nations, sponsored an assessment of the Earth's ecosystems. And in a nutshell, ecosystems provide a lot of value and functions that we value, like food, clean water, habitat for wildlife, opportunities for to recreate, commercial value, and so on and so forth. And because we recognize all these benefits, it's recognized that these ecosystems provide a service to people. So that's the term ecosystem services. It's a term of art recognizing those benefits that the ecosystem provides to humans. And there's different categorizations of ecosystem services. The general one out of the Millennium Assessment is supporting, provisioning, regulating, and cultural. But you can also update. There's other ways to look at these types of benefits. A general way to look at ecosystem service benefits is that you have an ecosystem, and that ecosystem is comprised of different types of biomes and habitats and so forth. And not only does it provide these ecosystem habitats for ecology, but it also provides human use services. Those human use services could be direct use. You could fish, dive, bird watch, boat. You could do all types of things in that environment. But there's also non-direct uses or passive uses. They have aesthetic value, bequest value for future generations, existence value. We value it because it might be a threatened endangered species, so that its existence is important. So there's different ways to look at these. And the main point to keep in mind is having that habitat and ecologies that there really serves as the underpinning for providing those human use services. And that's really was the purpose of this graph. When we think about it, a real concept of ecosystem services, and this is important in that it's not just a point in time estimate. You have a habitat provides value today, it provides value tomorrow, 10 years from today, potentially 100 years into the future, 1,000 years. So a habitat provides value over time. And there's that baseline can change periodically due to a variety of different types of impacts or different types of action, seasonally, seasonal attributes can change how those vary over time. And what happens is in times when we look at an action that might affect the environment, you could get a loss of those services over time. So these methods that we look at allow us to calculate and quantify what is that area under that curve, that potential impact associated with an action. At the same token, if we have a option that will provide a benefit, an enhancement project, for example, augmentation, things that create habitat, might create value above and beyond the baseline. It also allows us to create, well, to calculate what are these benefits. And it uses this in terms of environmental metrics. So it's a services provide per hectare per year as an example for different types of attributes. And then you also look at greenhouse gas emissions and those types of factors. When we think about the emerging science, and when I mentioned OSPA earlier, 25 years ago, 30 years ago, the default is you want to remove it below the mud line. And recently, I'd say in the past 10 to 15 years, there's been a significant amount of emerging science. We know that hard structure is a limiting factor in the oceans. Natural reef habitat is declining. And a lot of the data shows that some of the areas that are most productive areas in the habitats are related to some of the offshore structures and the subsea structures. And it's not only that they provide value for fish, but you have benthos that attracts fish, which in turn attracts marine mammals. And there's a lot of connectivity given 700 some jackets in the North Sea. So these do have some connectivity in terms of from ecological benefits. And a lot of this information is the Insight program, which I'm sure many of you are familiar with, is evaluating and looking at a variety of these different types of attributes of subsea structures. So we're really looking at what are some of the decisions we can make for decommissioning, for everything from complete removal to leave in situ to a variety of potential partial removals options in between. And then what are the long-term ramifications of those? When we think about, and I mentioned the productivity, and this is just a study that was done that looked at secondary fish production associated with habitats across the world. In this case, and I'm going to circle a common area. In this case, there's some work done off the California coast, where you look at the secondary fish production of soft bottom habitat, which is really the majority of the habitat in the oceans. But then you get deep rocky reefs can actually create a little bit more beneficial value. Estuaries as well provide additional value. And artificial rocky reefs have also been created a significant amount of value. But when we looked at that production, and when that production was looked at for a variety of these oil platforms off California, and quite a few platforms, the fish production is some of the highest recorded in habitats within the ocean. So it's an important aspect. And again, it all comes to, supply and demand. And when you think about hard structure, it's a scarce resource. So there's a lot of soft mud, and so it's versus an abundant resource. So that's really one of the things to consider about what is the value of hard structure in the ocean. And a lot of work that's been done looks at marine mammals, and the fact that marine mammals are attracted because there's fish there. The marine mammals follow, and there's different times of the year and different times during the day that they'll actually use a lot of these facilities as feeding stations. I work closely with Ocean Science Consulting in Scotland as well, and they do a lot of work, primarily on marine mammals acoustics and demonstrating a lot of the value that these subsea structures provide. The one thing as well to think about, so when we have this value, and this is just a conceptual one, we know baseline isn't constant or horizontal, but when we think about decommissioning, and if there's a point in time when you do a full removal, don't just lose that value today when you do a full removal of the ecology that's associated with it. You lose it from now into the future for as long as that habitat would exist. So the question is, there's values there that not just to our present, to us, to our present generation, but also intergenerational value to our kids and our kids' kids. What happens to all these values in the future? And it's not just the ecological value. There's commercial value tied to these populations. There's could be recreational value, a wide variety of different types of social values associated with this. So net environmental benefit analysis is a method that's really was developed to compare between alternatives and is a risk benefit. What are the risks, and then what are the benefits, and how do we make decisions? This is one of the first papers published, the original framework with Oak Ridge National Laboratory in US EPA risk assessor. This was in 2003. In 2004, we republished that in the Journal of Environmental Management, but actually removed the word petroleum because it really didn't matter whether it was petroleum, but really any action that is affecting a site, whether it be a restoration site or a mediation site, any physical action that affects the environment. We know these methods that we can quantify and look at these changes and how does this change these ecological services as well as the related human use services associated with them. In sort of an evolution, that was in 2004. In 2006, I wrote a chapter in the Interstate Technical Regulatory Council guidance on promoting and planning ecological reuse of sites that have different structure and so forth, and how can we manage site risk, but at the same time maximize benefits. And then in 2007, worked actually for the United States Environmental Protection Agency on a project and demonstrating what are these methods to quantify the economics, the environmental economics and the social economics of actions that affect the environment. What kind of metrics do we look at? Then actually did a lot of work for Department of Defense, for the Army, Navy, Air Force, throughout the United States on a variety of different sites, because they're looking at these sites have been protected for a long time, and now if they're going to go through and manage the cleanup as part of their closure process, this played an important role in understanding what are the values, because these are habitats that were protected, a lot of special species, on these places, just like you have with a lot of the offshore platforms with the exclusion zones. The EPA Science Advisory Board took that original framework and republished the framework within this document in 2009 on valuing the protection of ecological systems and services in the importance of making these considerations in risk management. Also, I mentioned, this process and this approach it's recognized was used by NOAA as part of work on the Deepwater Horizon, and as well in the Environmental Liabilities Directive. These methods on looking at services in a service-to-service approach are the preferred method within the EU Environmental Liabilities Directive, and looking at impacts and so on and so forth. And I've written a chapter in that book on the experience with restoration of environmental damage, which really talks about the evolution of these tools that really fell out of the Exxon Valdez work, and which really talked about why did we need these tools in the first place? Well, when you had a big impact, how can you figure out, well, how much should we spend, or what is the in this case, the responsible party owe the public for these impacts? Well, there wasn't a good method to quantify ecological values and social values. So how do you actually put a price on ecological metrics or ecological values? And it really became the point of translating that information instead of talking about dollars, because it didn't matter how much money you spend to do something. It's really the benefit that the public gets at the end of the day. Because two projects could cost the same amount of money to implement, but one could, when you convert those to the environmental metrics, one might generate 10 to 100 times the value as another project. So it's not the money that's spent, it's the benefit the public gets at the end of the day that's important. So the purpose of this whole approach is we want to maximize the ecosystem service benefits to the public while managing site risks. That's the main goal. Cost is basically, in the video I'm going to show later, we'll talk a little bit about this, but cost is a secondary parameter. We're really trying to focus on maximizing the benefits and managing the risks. When you do that, then the costs fall out to help support, or really the cost to implement that alternative that does maximize those benefits and manage the site risks. The approach is developed to be transparent. It's objective. It's scientifically defendable. The methods were upheld in federal courts in Florida, and I worked on some of the first cases of its application in the UK. And it's really a focus a lot more on quantification of options. And what we do with this approach is we incorporate this approach, just like with standard comparative assessment, is incorporate safety risks, environmental risks, benefits, societal, technical, and cost aspects. And when I do this analysis, and when this analysis is done irrespective of the constraints of the regulations, because regulations that were developed 25 years ago, things change. We learn a lot more from science, what's really going on, and do those regulations really apply, or do they need to be reconsidered based on what we know about the ecosystem? The other thing this approach does is it does not offer initially it doesn't offer upfront ranking or weighting of variables. And I'll talk a little bit about that later, because you don't want to introduce any subjectivity or bias into the process up front. You want to be able to see, what does the science say? Now, you can look at a lot of these metrics, and when you're done and running through this and do the evaluation of looking at the initial metrics without the ranking and weighting, there is an opportunity to go ahead and, with stakeholders, if you feel that, it's appropriate to rank or weight any of those different values. When we implement this approach, we identify what are the issues and risks. Is there a navigation risk? Is there a potential remnant chemical risk? Is there a trawling risk? Is there stability risk. What are the risks associated with the different options? And we understand what are the options we want to look at. Do you want to, look at a full removal, and we also look at leave in situ, but we also look at a variety of different intermediate types of options. Could be toppling, could be doing a partial removal at different depth ranges. And then we also want to understand and identify, well, what metrics are we going to use to be compared? And then I'll talk a little bit about those. And based on those metrics, for the different options, we want to predict, well, what are these metrics going to look like if I implement that option? And the goal is to understand, is there a break point where we go through this transition from one end of the spectrum of full removal to no removal? Where's the break point where it says, well, there's only maybe a certain point where we want to go, where we might actually be causing more harm than good with that option. And we're really just trying to balance the trade-offs in regards to the risks and the public benefits. And at the same time, like as I mentioned, secondarily, it address costs. There's a lot of potential metrics that we can use in this approach. And these metrics can be adjusted and modified as necessary. There's a lot of environmental metrics that we can look at, short and long-term risks. I won't go into these because the video will cover some of these. Look at technical feasibility, health and safety risks, onshore and offshore. Look at economic factors as well. And as well, understand what are some of the potential social issues. Then, it's really a desktop study with the exception of needing to analyze really ROV surveys and so forth. It's one thing to show people, it's one thing to tell people that, and our stakeholders that, hey, this is valuable. It's another thing to show them and demonstrate it and look at that information for a site. But it's pretty much a desktop removal or a desktop study. We look at what options with and without an exclusion zone. This is important because they're protected areas. If you remove that exclusion zone, what could it affect? In this case, you can see that, here's some of the different other options that you might have. If you do a partial removal, will you reef that potentially nearby, or will you take it onshore to recycle or do full removal? I thought this was an interesting article, came out in September of 2020, and Greenpeace is dropping boulders in the North Sea to stop illegal fishing. So there's, because it's in a protected zone, and trawling was, they're looking at the fact that trawlers might be entering some of these zones, and they understand that it's valuable and actually creating some hard structure, which is a good thing. NEBA, when we think about NEBA, you're really, it's a risk management approach. As you get more intrusive from left to right, from one option to the next, you have a high risk. And then as you implement your options, you reduce your risk. And you've seen similar cost benefit curves. And that's really what we look at managing here. And then we also look at, in a lot of cases, it's, well, we're going to spend money to reduce risks, and we see how the costs increase. But from you get a big drop in risk from, in this case, to option one, but option 1 to 2, got a marginal change in risk, marginal decrease, but a much greater increase in cost. And you really got a marginal increase in the risk, even getting more intrusive, but your costs keep going up. And the one factor that typically hasn't entered into that equation is quantitatively being able to demonstrate, well, what are the impacts on the ecological service values? How do those change? In this case, you have losses. And because you have those ecological losses, you can have human use service losses. So is there a break point where, well, going from this option to this option, does it make sense to spend that much more money, have a marginal change in risk, but create impacts that basically potentially outweigh that potential risk? So that's really how this works in a nutshell. And this is just a conceptual example of some of the output. In this case, when you look at, in this case, it was in situ management with an exclusion zone. And then maybe doing a partial removal at 85 feet, which is in the US, 55 meters, the IMO standard. You might do it at a derogation depth, as well as full removal below the mud line. And what we could do is say, well, we can see how these benefits change as you get more intrusive, how they decrease, your risks get higher. So is there a point where might you make this decision? And it's understanding what are these risks and making a risk management decision. Well, maybe this is an unacceptable risk, that what the best thing to do in this case would be to do this at the 26 meter area and so forth. The point of that graph is really thinking about OSPAR, where the starting point of OSPAR is full removal and then going to a derogation depth. Whereas when we start considering the ecosystem service benefits, we sort of really look at and start at the left side of that equation and say, okay, how do we move from left to right? So it's really a different directional approach. And the video is going to talk about this and the difference between some of the typical comparative assessments, like in the UK. They're both similar. They cover the 5 criteria. The NEBA-CA, it really focuses more on quantified metrics. And the typical CA focuses on risk, doesn't focus on the benefits. And we focus a lot on the benefits and the losses. That time value, that intergenerational value, that flow of value is another thing we look at. It's not just a snapshot in time. And typical CAs, there's a lot of guidance that allows for a lot of different ways for that to be produced, and which sometimes may have different interpretations and so forth. And it does, the typical CAs, you can adjust and rank things up front, but again, that can increase bias and subjectivity based on who's in the room and less transparency. The NEBA-CA, again, we want it to be quantitative. It's transparent on how everything's developed. We don't initially do the ranking or weighting, although you could incorporate that after you go through the first steps so that everybody can see what the science says. And we try to do it in graphic displays that are easy to understand. You've seen the precautionary principle. It's the bedrock of EU policy, environmental policy. If an action or policy has a risk of causing harm to the public or to the environment, in the absence of scientific consensus that it's not harmful, the burden of proof that it's not harmful falls on those taking the action. So policymakers have discretionary decision-making ability. And what this principle implies that there's a social responsibility to protect the public from exposure to harm when scientific investigation has found a plausible risk. And right now, the scientific investigation has found that there's a plausible risk to the impact of removing a platform on the ecosystem, the related human use values. What happens to that over time? What are those intergenerational values? There's a lot of information there that, well, there's a potential that there could be a risk there. Could affect future commercial fishing because they provide stock protection areas. So is OSPAR correct? Maybe a little outdated, maybe needs a change and have a little more flexibility on how you can manage these types of things. I'm not going to go some of the key attributes. The video will cover that. And but really it's evaluating the flow of these services over time, easily understandable graphics. Don't want to overweight past precedent because we did it 25 years ago. Is it necessarily better today? We want to do the right thing. We want to consider benefits along with risks, and at the same time, it allows us to manage costs. I mean, manage if the UK government isn't spending their portion on actually creating harm in the environment, and actually we're able to use that money to actually do social programs and increase other benefits that have even a long-term intergenerational value as well. So there's a lot of different things to consider here. And this is, I think, my last slide. And I was asked to do a presentation by the state of California on offshore decommissioning in this approach. And because they wanted, and I wanted to get the concept across it was developed, the video was developed for the public. So regulators, operators, and academia, everybody that was there. Says it was developed to try to provide an example of what this looks like. And so with that, I'm going to go ahead and play a video, and you should be able to hear it and check your volume. And it's about 13 minutes, and then I'll answer some questions when it's over.
Oceans provide habitats for fish, marine mammals, and invertebrates such as mussels, oysters, and shrimp. It is no surprise that humans benefit from these habitats in a variety of ways. Because it is widely recognized that ecosystems provide resources and functions that we value, and because we value these benefits, we recognize that ecosystems provide a service to people. Hence the term ecosystem services, referring to the benefits that ecosystems provide to humans. These habitats support growth, reproduction, and biodiversity of marine life, associated food production through commercial fishing, and human use activities such as recreational fishing and diving, as well as social and cultural benefits, to name a few. Offshore oil and gas structures come in a variety of shapes and sizes and are used to support the extraction of oil and gas. Once a platform consisting of the jacket and topside and associated seabed facilities is installed, regulatory agencies, working with offshore oil and gas operators, implement exclusion zones around these structures. The exclusion zone prohibits non-authorized vessels, helps to protect the oil and gas facilities, the health and safety of commercial users, and the seabed. For example, 500-meter exclusion zones in the North Sea are in effect through the life of the infrastructure and deter commercial activities like shipping and trawling from occurring within certain distances of the infrastructure. Marine communities and habitats within the exclusion zone have been afforded protection from trawl fishing disturbance for decades, acting as marine protected areas. The habitats within exclusion zones have evolved over time. The hard substrate provided by the jacket and associated seabed facilities attracts colonizing invertebrates that in turn attract fish, marine mammals, reptiles, and other marine life, creating a functioning ecological community. In most cases, mollusks and other species that colonize the upper levels of the jacket fall to the seabed after they die, which combine with the deposited sediments to develop a hard calcium shell hash layer on top of the sediments under the jacket. The shell hash layer creates additional hard structure for colonizing organisms. As the jacket and shell hash habitat matures, it promotes the deposition of organic matter around the jacket. The increased input of organic matter to the seabed community, as well as protection from bottom trawling, creates a productive halo effect area surrounding the jacket that can be much larger than the jacket footprint itself. The combination of hard structure associated with a jacket, shell hash layer, and halo effect area creates a habitat that has been shown to be significantly more productive when compared to surrounding soft bottom habitats. There is growing evidence that subsea infrastructure not only attracts fish, but also operates as a center of fish production, whereby new biomass is being generated at the site, and fish population densities are enhanced by the presence of subsea infrastructure. As an example, secondary fish production associated with oil and gas platform jackets off the coast of California have been shown to be 18 to 150 times that of California's soft bottom habitat, and as well have greater productivity when compared to natural reefs across the world. Thus, aside from protecting marine life and seabed habitats, subsea infrastructure within the exclusion zone is providing both fish stock protection and replenishment. Not only are marine communities thriving around these subsea structures, developing science indicates that marine communities interconnect between multiple subsea structures. In the North Sea and Australia, it has been demonstrated that marine mammals, including protected species such as the harbor porpoise, use subsea oil and gas infrastructure as feeding grounds, with both daily and seasonal patterns. The protection and productivity of these structures are therefore benefiting significant species such as dolphins, whales, sea turtles, seals, and others. Net environmental benefit analysis studies in the North Sea, Australia, Gulf of Mexico, and Southeast Asia lead us to conclude that the increased productivity associated with these subsea structures is not just limited to California, but to subsea structure worldwide, creating benefits in the face of decreasing natural reef habitat and increased commercial fishing pressures. Offshore oil platform jackets are projected to last for hundreds to over 1,000 years. These habitats not only provide benefits to us today, but can provide these benefits for many generations to come. How should we decommission these structures after they reach the end of their production life? A study designed to evaluate potential decommissioning options for subsea infrastructure is termed a comparative assessment. Comparative assessment studies, to date, generally consider environmental, health and safety, technical, financial, and societal factors associated with decommissioning options. Comparative assessments incorporate preference ranking schemes that focus on risks. However, they do not fully consider the ecosystem service benefits that the infrastructure provides today and can provide for decades and centuries into the future. Understanding the scientific weight of evidence regarding the ecosystem services provided by the presence of subsea infrastructure, declines in natural reef areas, and climate adaptation considerations, it is imperative to understand and consider the benefits associated with these developed ecosystems and the potential impact, positive and negative, that decommissioning options can have on these ecosystem services. To understand the potential ramifications to ecosystem service benefits associated with implementation of various decommissioning options, we introduce here a net environmental benefit analysis-based comparative assessment, hereafter referred to as a NEBA-based comparative assessment, or NEBA-CA. The goal of a NEBA-CA is to maximize the ecosystem service benefits to the public while managing site risks. A NEBA-based comparative assessment not only considers environmental, health and safety, technical, financial, and societal factors like standard comparative assessment processes, but crucially includes consideration of the ecosystem service benefits and the flow of these benefits over time to current and future generations. A NEBA-CA primarily incorporates a variety of quantified ecosystem service benefit and risk metrics to estimate how various decommissioning options may affect human health and the environment to inform decision-making. The NEBA-CA is based on methods that are quantitative, scientifically defendable, transparent, objective, and litigation tested, and focuses on a variety of metrics and how these metrics change with the implementation of various actions. These include, but are not limited to, multiple metrics reflecting ecological habitat value, human uses of the sea, greenhouse gas emissions and other air pollutants, ecological and human health risks, navigation, trawling, and implementation health and safety risks, and technical removal risks. Additionally, option implementation costs are also evaluated. However, cost is considered as a secondary evaluation metric within a NEBA-CA, since the focus is on maximizing benefits to the public while managing site risks. Let's look at potential options for decommissioning and the trade-offs associated with these options from both a benefit and risk standpoint. It should be noted that, regardless of the decommissioning option selected, the topside portion is typically removed and transported to shore to be reused or recycled. Prior to topside removal, the production wells are plugged with cement, and the pipes from the wells to the platform, as well as pipelines that carry oil and gas away to shore, are flushed of hydrocarbons to regulatory standards, then filled with seawater. Decommissioning options for the jacket, as well as other subsea facilities, can range from a full removal action to a protect-in-place option, with various partial removal options in between. The protect-in-place scenario is depicted here, with the exclusion zone remaining. Keeping the exclusion zone serves to protect and conserve the habitat while also mitigating risks to navigation and trawling, as well as seabed disturbance. Since less decommissioning effort is required under this option, implementation risks, greenhouse gas emissions, and costs are lowest when compared to other options. Full removal of the jacket is also an option where the entire structure is cut, usually in multiple sections, below the mudline, and taken to shore to be reused or recycled. This option eliminates navigation risk, trawling risk, and the need for an exclusion zone. However, it does so at the expense of the environment through adverse impacts to ecosystem service benefits related to hard structure habitat loss, associated fish stock protection, commercial fish stock abundance, and long-term preservation value of the ecosystem. This means that the ecological and human use benefits that are protected and provide value today and for hundreds of years into the future would be lost, thus affecting current and future generations. Additionally, due to the level of effort involved in full removal, implementation health and safety risks, greenhouse gas emissions, and costs are likely to be highest for a full removal option. Within the bounds of the protect-in-place and full removal options, there are a variety of partial removal options that can be considered. Partial removal options include actions where a designated section of a jacket or equipment component is removed and either transported to shore to be recycled, reefed near the jacket, or reefed at an alternate location. Additionally, there are different methods that can be employed for removing or reefing sections of the platform. For example, cutting and direct lifting versus toppling. It is important to note that maintaining the exclusion zone for protect in place and partial removal options manages navigation and trawling risks, provides fish stock protection for all fish at the site, including threatened and endangered species, and other protected fish, not just commercial and recreational fish, and reduces impacts to fish, sea turtles, and marine mammals associated with incidental trawling bycatch. A NEBA-based comparative assessment also provides flexibility in evaluating a range of potential options and allows for consideration of cutting depths, cutting methods, and cut section disposition, such as reefing or recycling. Based upon our NEBA-based comparative assessment case studies, decommissioning actions pose a plausible risk to ecosystem service benefits. Regulations, guidance, and decisions governing subsea infrastructure decommissioning should consider the potential for adverse near-term and long-term risks through adherence to the precautionary principle. That is, if an action or policy has suspected risk of causing harm to the public or environment, in the absence of scientific consensus, the burden of proof that it is not harmful falls on those taking the action. Do we have scientific consensus that there are no risks to the ecosystem and associated human uses of the sea with removal of hard structure? Complex, multifaceted decisions must address many questions and balance competing criteria to achieve the least overall harm outcome. Good-intentioned but narrow-focused decommissioning option evaluations have the potential to lead to unintended consequences. Since a decommissioning action must be taken, robust scientific analysis within comparative assessment underpins sound least overall harm option decisions. Comparative assessment methods differ, and while they may lead to the same conclusions, some situations may not. The NEBA-based comparative assessment specifically supplements, as described, a standard comparative assessment in 3 key ways, any of which may be crucial in identifying and recommending the least overall harm decommissioning action. First, the NEBA-based comparative assessment incorporates ecosystem service benefits and the flow of these benefits over time. Second, it is primarily quantitative and does not rely on ranking or weighting schemes that can introduce subjectivity and bias into the option selection process. And third, provides objectivity. That is, rather than having preference weights imposed by others, provides transparency to stakeholders on inputs to the comparative assessment. It should be noted that the starting point for discussion of decommissioning options is distinctly different when comparing a NEBA-based comparative assessment and a standard CA process. A NEBA-CA for subsea structure is a site-by-site analysis, since overall ecosystem value can vary by structure and location. The question we must ask ourselves is, in the face of losses of natural hard reef habitat and increased commercial fishing pressures, will removal of subsea infrastructure adversely affect long-term fish stock protection and associated ecosystem service benefits for future generations?
Well, can everybody, that's the end of the video, obviously. And I think now I can take some questions.